Hi everyone, in this video we're going to evaluate another series. This time it is a sum where I goes from 0 up to n of I times x to the I, and I've denoted this as Sn. So the first thing I want to do towards evaluating this is simply to note that it looks very much like the following series. The sum where I goes from 0 to n of just x to the power of I. Now this is a standard result, it's called the geometric series, and it is given by 1 minus x to the n plus 1 over 1 minus x. Okay, so you may have seen that before. If not, I do have a video on where this comes from. And so now we've got to figure out how this geometric series is related to the series that we're trying to evaluate here. Now notice that the series we're trying to evaluate has a prefactor of I in front of the x, right? And also notice that the geometric series has a power of I. The exponent of x is I. Okay, so one way we can bring down a number from an exponent to a prefactor is by differentiating, right? That's just the power rule of differentiation. And so let's try doing that. Let's take our differential operator, d by dx, and apply it to this equation for the geometric series. Okay, so if we differentiate the left-hand side, we can just differentiate it term by term, so we can keep this summation. And if we differentiate x to the I, we get I times x to the I minus 1. Okay, so this looks very much like what we're trying to calculate, right? It's just off by a factor of x because we have an I minus 1 instead of an I. But that's fine, we can just evaluate this and then multiply up by a factor of x at the end to turn it into the series that we actually want. Now we have to differentiate the right-hand side of our geometric series equation. And I'm going to use the quotient rule to do that, which tells us that if we have two functions, u and v, we divide u by v and differentiate that. I'm showing differentiation with a prime here. What you get is u prime v minus u v prime, and the whole thing is divided by v squared. So here, our right-hand side is of this form where u is 1 minus x to the n plus 1 and v is 1 minus x. Okay, so let's just apply this, this formula. And so u prime, well, we just differentiate the numerator and we get minus n plus 1 x to the n. Okay, and then we have to multiply that by our v, which is 1 minus x. Then we have to subtract off uv prime. Okay, and well, u is just 1 minus x to the n plus 1. V prime is the derivative of 1 minus x, which is just minus 1. And so what we can do is just, instead of saying times by minus 1, we can just change this subtraction in the middle into a plus, right? So we just have to divide that whole thing by v squared, which is 1 minus x all squared. So let's just tidy up this expression a bit, right? So from this first term, let's expand that out into two terms. So looking at this 1 here, we get minus n plus 1 x to the n. And then looking at this minus x, we get another term which is going to be plus n plus 1 x to the n plus 1. And then this stuff at the end of the numerator is still around. We've got 1 minus x to the n plus 1. And still, all of that is divided by 1 minus x squared. Okay, so how can we simplify this even more? Well, we've got a minus x to the n plus 1 at the end, and then we also have a plus x to the n plus 1 from here, right? So we can get rid of that and that, okay, because they cancel each other out. And so, what does this simplify to? Well, we've got, from our middle term, we've got nx to the n plus 1, right? Then we subtract off n plus 1, x to the n, and then we add on 1 at the end, and then we still divide everything by 1 minus x squared. 1 minus x squared. And so all we have to do now is multiply up by that missing factor of x, remember, because we have an I minus 1 as our exponent of x here. So Sn is just going to be x times this, which is n x to the n plus 2. That's a 2n plus 2 minus n plus 1 x to the n plus 1, and then we just add on x, okay? And then, again, all of that is divided by 1 minus x squared. Okay, And the last thing we can do is consider, as we did for the geometric series, we can consider the limit as n goes to infinity, right? So the limit where we're summing together an infinite number of terms. Consider the limit of Sn, and we're going to write that as S subscript infinity. What's going to happen? Well, we can make a similar argument to what we did for the geometric series case, which is that we can only do this if the modulus of x is less than 1, as in if x is between -1 and +1, because in that case, right, x to the I is getting smaller and smaller each time you multiply x by itself again, right? If it's less than 1, it's getting smaller and smaller and approaching 0. So in that case, we can actually sum together an infinite number of terms. Okay, so how can we actually evaluate this? Well, we've got to look at our Sn expression, and I should also note down that this is only applicable if the modulus of x is less than 1, right? In that case, let's look at this first term, nx to the n plus 2. Well, it's not necessarily immediately obvious what happens as this goes to infinity, because n is getting bigger and bigger, but x to the n plus 2 is getting smaller and smaller, because mod x is less than 1. In fact, it turns out that this term does go to 0, which is essentially because the n is growing linearly, whereas the x to the n plus 2 is shrinking exponentially, right? And this exponential shrinking, it happens kind of faster than the linear growth, and so that the exponential shrinking wins, and this term goes to 0. And similarly for this middle term here, right? N plus 1 grows linearly, whereas x to the n plus 1 shrinks exponentially, so the exponential kind of wins. And so if we take the limit as n goes to infinity, you're just left with this x at the end divided by 1 minus x squared. We could have done that, I guess, in a slightly easier way by taking the limit as n goes to infinity directly from the geometric series and just differentiating 1 over 1 minus x, but you end up with the same result either way. So that's how you can evaluate. You can use the geometric series standard result to evaluate this other kind of interesting series.